Okay, let's go ahead and get started. There's a sign-in sheet going around for attendance. Make sure you get it. You have any questions before we begin? Hi.
I was here last time, but just never received this.
Okay. Last time we covered limits, and we looked at how to solve them algebraically when you have the form of 0 over 0. Not always you're able to, in fact, do these kind of algebraic techniques to solve it, but when you can, it's nice. Someone asked a question. I added this one in about what happens when it's not 0 over 0. What if the denominator is going to 0, but the numerator is going to something else? And I explained there. And then we left off. We weren't finished with this. We still have the squeeze theorem. But what I'm going to do is just record a separate, shorter recording just of this. It should take like 10 to 15 minutes. Explain what it is, using it in an example, explain why we care about it, and then see it used in action. This comes into play when we want to say later on that the derivative of sine is cosine, and without knowing the L'Hopital's rule, the ability to be able to show that this limit of sine x over x as x goes to 0 is 1 is necessary in the definition. And so I'll record those 3 slides in a separate recording and then post them. I have started to record lectures, and so the last lecture we had is here, and then I'll populate it. The things that are here were what I recorded last semester. I'll probably just leave those up. And then I'll just fill in the gaps here. I'll make some space and fill in the gaps. But don't use this as a substitute to showing up to class, though. Make sure you still show up to class. This week you have a hand-in homework due on Friday. Okay. And it's still over review, but then there's also the limit material that we covered last week is on there as well. I put up the next homework assignment that we do the following Friday over what we are covering this week. Where are we at as far as the calendar? We're covering limits and how that affects continuity in section 2.5, and then in section 2.6, limits at infinity. And so if there aren't any other questions, we'll just go ahead and move on then. All right, great. So make sure you sign your name in to the sign-in sheet. So in section 2.5, we look at continuity. What does it mean? A function is called continuous at a point, x equals a, if the following is true. There's 2 parts, basically, 2 equalities that need to be true. The first thing is just that the left-hand limit has to equal the right-hand limit. And that just says basically that the limit needs to exist there. We talked about that about a week ago. If the left-hand and right-hand limit agree, then that means that the limit exists. There's one more equality, though. Not only that, we add an extra equality onto that. It has to equal the actual function value at x equals a. So on one hand, the limit has to exist, and on the other hand, it has to be equal to the function value. That's what it means to be continuous at a point. Okay, so you can't have that strange situation that we had before where we take and remove the point and put it someplace else, or not even make it have an identity at all. You can't have that. We need it to be where it's going from the left and where it's going from the right. We need them to agree, and we need the function value to be there. That same capital L that they're headed towards needs to be the function value f at a. Okay, that's what it means to be continuous at a point. All right. In the big picture, though, if you want to be continuous, we're going to look at later, continuous over a whole, interval of points. Basically, as you draw the graph of the function, you just need to make sure that you don't lift whatever you're writing with. Then you're continuous. And so I like to think about it as not being broken. The fact that you're continuous means that the graph isn't broken, and it's and officially it means exactly what we have here. Any questions about the official definition of continuity at a point? Yes?
It's not a question about that. It's just, could you turn the lights down at the front?
I don't even know if I can. That's a good question. Can I turn the lights down in front of it? Good question. These lights here? I don't know. Is that good? That worked out well. What was that? I gotta remember that. Okay. Great. It's not too dark. You still can see. It's good. Okay. Yeah. Limit from the left equals limit from the right, and that's the function value. If I give you a graph, it'll be not too difficult to tell whether it's continuous, but if I give you a function, it'll be a little more difficult to tell, whether it's continuous or not. And so at first we'll rely heavily on being able to look at a graph, but then after that we'll figure out how to do it if there's no graph. Okay, what does it look like for a function? If I'm looking at a graph, then what does it mean for a function not to be continuous? The word we say is discontinuous. And there'll be three different types. A function will not be continuous if we had what we had before, where, okay, yeah, the left-hand limit and the right-hand limit are green, but the function value has been removed and maybe not even put someplace else, or maybe later put someplace else. But, this type of discontinuity has the whole limit from the left equaling the limit from the right, but it doesn't have the function value being that same limit. And so this is a removable discontinuity. So if you're looking at a graph and you see this is definitely a place where your function is not continuous. A more obvious type of discontinuity is called a jump discontinuity. You have this function where from the left-hand limit, you get one value, but from the right-hand limit, you get a different value. There's this jump in the function. This is a special kind of function here. This is a double bar. It's called the greatest integer function. If we had time, I'd go over that. What is it now? It's not letting me write. It's a problem. I don't. It's weird. Wow. Okay. Strange. Why is that? I'm sorry. 1 second. Wow. Kind of throws a monkey wrench in the plans. Okay. So, really? Wow. I was still going to work it out. All right, so it's called the greatest integer function. And what it does, whatever number's on the inside, you simply chop off the decimal part and you just get the integer part. The greatest integer less than or equal to whatever number's on the inside. And so it has this effect where if I'm between 0 and 1, then the function value is 0. But if I'm between 1 and 2, the function value is 1, and so on. It has this sort of jump effect to it. And it's used a lot if you're trying to model how a taxi cab charges you rates. For a certain distance, it's the same rate. But then all of a sudden, you see the meter jump up and you have a different rate. And so it's called the greatest integer function, if you ever see it before. That's a double square bracket bar, a double bar square bracket. And so anyway, this type of discontinuity that this function exhibits is called a jump discontinuity. And then finally, if your function just goes off to infinity in any manner from left or right, whether it goes off to positive infinity or negative infinity, then that's just an infinite discontinuity. And so your function is discontinuous at any type of vertical asymptote. Okay, so if I give you a graph, you just look for these types of things and say, okay, it's not continuous at this particular point. We want to be able to say, well, what happens how do you get continuity at a bunch of points? And how do I know if I don't have a graph, how do I know whether it's continuous or not? And so that's where we're headed. Any questions on this slide? All right, great. You could be, this kind of isn't focused on too much in our textbook, but you can be continuous from one side. So the whole part about being left-hand limit equaling right-hand limit, you can throw that out. And as long as your left-hand limit is the function value, then you're continuous from the left. Or if your right-hand limit is the function value, then you're continuous from the right. And so you just ignore everything that's going on from the one side and focus on the other side. And so here's a picture of that. An example where on some of these points we're continuous from only one side. And so this isn't from our textbook. It says exercise 3, but it's actually from a different textbook. And so the question that we want to say is, just by looking at it, just by eyeballing it, based on the last slide, how do I know where the function is discontinuous at? So as I go from left to right, the first x value that I see that I'm discontinuous at is -4. I have this point being removed. That's a removable discontinuity at -4. Keep going. You're continuous for all the ones in between -4 and -2. What type of discontinuity at -2? Jump discontinuity. The left-hand limit is not equal to the right-hand limit. You have this jump discontinuity at x equals -2. It's tempting to say that there's a discontinuity at x equals 0, but it's not. The function is continuous there. There's nothing wrong. The left-hand limit does equal the right-hand limit, and there is a function value there. But sharp points like that, we're going to later, when it comes time to talk about the derivative, we're going to say that those are places where you cannot take the derivative at. And so there's analogous to continuity is differentiability, being able to take the derivative. And at a sharp point, you're not allowed. You're not going to be able to take the derivative. So it is continuous there, though. And so we continue on all the way up to 2. And we have another discontinuity. That's a jump discontinuity at 2. And then at 4, what's meant to be is that this thing is going off to -infinity. So that's another discontinuity. That's an infinite discontinuity at 4. Okay, great. So that should be not too bad if I give you a graph. You still are able to recover one-sided continuity on some of these. And so from the left, as long as where you're headed to from the left is where the point is at, then you're continuous from the left. So not at -4, where you're headed to, the point isn't there. But at -2, where you're headed to, the point is there. So you're continuous from the left at -2. Okay, but no other place of these discontinuities, you aren't able to recover one-sided continuity from the left at least. From the right, though, it's going to occur at 2. Where you're going to from the right is where the point is at, where the function value is, and also at 4, where you're going to from the right is where the function value is. So we're not going to make too much big deal out of this one-sided continuity. I'd rather focus on the bigger picture of just a function being continuous, but it is a possibility for you to still recover. Although you are discontinuous, you are able sometimes to still be able to recover one-sided continuity. Question, yes? As you're approaching from that side, when I say where you're going to, as you travel along the graph of the function from that side, you're headed to the actual function value. So at -2, as I travel along the graph of the function from the left-hand side, I'm headed towards the actual function value. So I'm continuous from the left. And at x equals 2, not from the left, but from the right, where I'm headed towards on the graph is where the function value is. So I'm continuous from the right. Good question. I see another hand up. We're good? All right. We're not going to make too much of a bigger deal out of that, but you should see it at least. One-sided continuity. Okay? We're going to be continuous on more than just one point. That's all we discussed so far is continuity at a single individual x value. Well, we want to be continuous on a bunch of x values. And so on a whole interval of x values, as long as you're continuous at every point that's in the interval, then you'll be continuous on that entire, interval. But showing this isn't the easy thing. If given a graph, it's fine, but when you're given a function, it's a little more difficult. Back to that same graph with arrows drawn in, we want to say, I want to be able to write on this. This isn't good. How can I write on this? Let's see, I don't know, let's see. I can't even delete this stuff? I can't even oh, it's a protected view. Oh, that's why. I don't want to protect it. I'm sorry. Talking to myself out loud. On the recording. What's the protected views? I just want to draw on it. The office has detected a problem with this file. Edit it may harm your computer. What? Whatever. Okay. There's always ways around things. If you like to take computers notes, you have some kind of tablet. There's this program called PDF Exchange Viewer, a free program, and it lets you write on PDFs. And so I'm going to. Oh wait, that's what I wanted. I'm going to write on the PDF just like you would if you were taking notes. I don't know. Let me just grab somewhere here. I should be able to find the. Yeah, here we go. All right, I'll blow it up. Don't worry. All right. I want to be able to. Okay. Sorry. Blow it up. Oh, here it is. State the intervals that the function is continuous on. So I'm going to take a screenshot here. You know, it's better. Let me just take a screenshot and work from that. That's weird. It won't let me. How do I change this thing? Edit anyway. Oh, there it is. I didn't see that option. Edit anyway? It's going to let me? Sorry. There we go. All right, because what I have on the slide is it's too involved. Like it tries to recover the one side and it uses square brackets sometimes. But I just want you to say, you know, give me the intervals, and I don't want you to have to worry about what kind of symbol to use on the left or the right. So that's kind of getting too technical. So basically, all these x values up to -4, the function is continuous for. So from -infinity up to -4. Okay. Sorry. State the intervals where the function is continuous. So that's one interval. And then from -4 up to -2. Between -2 and 2. From 2 to 4. And from 4 to infinity. So if you're looking at a graph, then it's not that bad. You just look for places where the function isn't broken at. Don't worry about what happens at these points. So I'll change the slide if you already have the full slides and you see square brackets being used sometimes. I don't want you to have to worry about that. It tries to recover left or right hand continuity and it uses a square brackets sometimes. It's too much detail. We don't need that much detail. I just want you to say I'm continuous for these, you know, group of x values, this interval here and here. The harder part though is if I give you not a graph, but if I give you a function and you don't have a graph, and I don't expect you to be able to jump from function to graph, how can you still answer the question, what intervals is the function continuous on? And that's what we want to be able to tackle. If you have a continuous function and you want to combine it with another continuous function, basically then it would be continuous on the overlap. So here's a function continuous at a point f, and another function g continuous at a point x equals a. I have the function f and g both continuous at a. Then if I add them, I'll be continuous at a. If I subtract them, I'll be continuous at a. Multiply them, I'll be continuous at a. If I divide them, I'll be continuous at a. Of course, you have to worry about division by 0, as long as that doesn't happen. And if I take one of them and multiply it by a number, I'll still be able to recover continuity at that particular x value. Okay. Here's the hardest way of combining functions is to do a composition of functions where you have one function plugged in as the input to the other function. And so this is the f of g of x version. So composition of functions, it's called. Hopefully you've seen some of that on the homework and how to deal with them. So we want to say, if I have a function like this, how do I know where it's continuous at? And at a point, at least, you just need to make sure that the inside point is a place where the outside function is continuous at. So g is the inside function, and g of a. And as long as the outside function f is continuous at that individual point, then the function will be continuous at that point. Okay, but this is all at a single point. And what we want more, though, is how to tell whether a random function that I give you is continuous and where it's continuous at. And that's misspelled. Jeez, I gotta fix that. Make a note. Oh wait. Yeah, there's an n missing there. I have to fix that. All right. Sorry. It's for myself, not for you. All right. So here's how we're going to do that. We're going to basically break it up into types of functions. Any type of function that we study, here's the deal. If we want to know where it's continuous at, it changes around and becomes the question of where's the domain of that function. As long as you have a point that's in your domain, then you'll be a point where you're continuous at. Some functions, like polynomial functions, they are continuous everywhere because they are defined everywhere. And so where you're continuous at is traded in for the question, what x values you're allowed to use. What is your domain? And so for all of these particular types of functions, rational functions, polynomial functions, root functions, trig functions, exponential log, and inverse trig functions, for all these types of functions that we deal with, the question of continuity becomes the question of domain. Okay. There is a eighth type of function, which maybe we'll have time to deal with, maybe we won't. It's called a hyperbolic trig function. And that's usually at the very, very end. It's possible we could just cover it. I might just record a lecture for you just to watch it, but I would not hold you responsible for it. It's something that you should see. I don't want you to get to a class that uses that and expects you to know it and not, had seen it before. But we'll see. Usually it's something that's dropped from the 103 syllabus in the interest of time. But that's the eighth type of function called a hyperbolic trig function. But this is the group of functions that we should know about. And so we should know enough about them now to be able to find their domain. And so where's this function continuous at means where is this function defined at? And so what is the domain of the function? It goes back to a pre-calc question. If you have this type of function is called a rational function, a polynomial divided by another polynomial. And so where is it defined at? And so when you have division, what do you worry about as far as the domain? Where the denominator could possibly be equal to 0. You can't have that. You can't have division by 0. So those x values have to be thrown out. So you focus all your attention on the denominator, and you want to set it equal to 0 and solve. That's factorable. So where does this thing equal to 0? X squared plus 5x plus 6 equals to 0. How does that factor? Both the signs are the same, and they're both positive. 3 and 2. Very good. You had factored it correctly if there was a minus in front of the 6. Or not. Oh, no, actually, I'm with that 5 there. Anyway, so x is equal to negative 3. You're not done. You have to find out, x plus 3 equals 0 or x plus 2 equals 0. So the culprits are negative 3 and negative 2. These are the guys that would cause your denominator to equal to 0. So you cannot have them in your domain, but you can have everything else. I'm okay, like on a test, for you just to say that. All real numbers except these two guys. Okay, my math lab might not like that. Of course, I know they don't. And so they'll want intervals. Okay, so I need to throw out these guys. How do I say everything else but these guys in interval notation? Oh, you have the answer? Yes.
Negative infinity to negative 3.
Very good.
No, you can't.
Hmm?
And then negative 2 infinity.
In between these two guys, and then negative 2 to infinity, yes. So basically, with in between union symbols, this is the entire real line with those two guys thrown out. Parentheses all the way throughout. If you use a square bracket, that means you can equal to it, so don't use a square bracket here. Right? So that would be the interval answer. But on a test, if you're writing it out, I'm not going to be picky like that. Just give me the words. It's perfect. Yes?
If you see it
Without the symbols? Without the unions? So you've seen square brackets around infinity?
No, around negative 2 and negative 3 without the interval.
So you would like to write this answer as negative? Huh? Like something like this?
Yeah, like the
Then the rest of that, and then something like this. Just remember, in your mind, square bracket means you can equal that. And as far as domain, that means you can use that number. And we can't. In this particular instance. But in other instances, we'll be able to use one of the numbers and not the other. So if you can use it, square bracket. If you can't, parentheses. All right. The symbol in the middle? This interval in the middle? If you're throwing out, then you need to include everything else. If it helps you, I think what you should do is draw a number line, basically, and think about officially taking these guys out, and everything else is good. So then I need the one in the middle then in this particular case. Yeah. And so I want from minus infinity up to -3, from -3 to -2, from -2 up to infinity. Yeah, good question. These are all good questions. More questions? Let me erase part of this so that the next question comes up and it doesn't get overwritten here. Let's see. I think it's gonna. Oh, good. Okay, good. So the next one. This isn't an easy one here. It looks deceptive. It looks like, oh, that's not that bad. It's just a square root. It turns out to be not too easy. So what do you worry about for domain for square roots? Having a negative underneath. You don't want that. Now, instead of finding where it's negative and throwing it out, kind of that negative approach that we did for the denominator, we're just going to use the easier approach, which is, okay, just make sure that it's positive. Force it to be positive. So take what's underneath, in this case, this guy here, 4x squared minus 9, and make it greater than or possibly equal to 0. It's okay to take the square root of 0 because that would just be 0. And so that's how you handle the domain for when there's a square root involved. Take what's underneath, make it greater than or equal to 0. But this is an easy question to solve. You can't just move the 9 over, divide by the 4, and then take a square root. That's okay if it's an equals, but not for the less than, greater, not for an inequality. You can't solve it so easily. And so here's what I recommend. I recommend a visual. So this is a parabola. Okay, it opens up just by looking at the first part, 4x squared. You can say that. Okay, the minus 9 is a shift down, a 9. And so there's two places where this parabola basically comes up and hits the x-axis. If I could find those two guys, right, if I could find out where it's equal to 0 at, then that can help me to say where, now I can look at this graph, and that can help me to say where it's positive at. I don't want the in-between, since this is a parabola that opens up. I don't want these guys in between. They make it negative. I don't want those guys. I want where it's positive at. Negative is below the x-axis and positive is above the x-axis for y values, and so that's what I want. And so when you're handling a quadratic and you're worried about the signs, my recommendation is to analyze it by thinking about what the graph should look like. Not an official graph or anything like that, just a sketch. And so where is it equal to 0 at? Now we could do that algebra and say that x squared is 9/4, or x is plus or minus 3/2. Okay, so negative 3/2 and positive 3/2. I just have to avoid being in between there because my parabola would be negative, my square root would be negative. Okay, so I have to avoid being in between. I avoid being in between. So I go from negative infinity up to negative 3/2. And to answer your question, we're going to use a square bracket here. I can equal that. I go from 3/2 up to infinity. And union symbol in between. That is the domain of that question. And that gets translated to be, that's where that function, that's the domain of that function. And then that is where that function is continuous at. Question, yes?
So why did you switch the greater than or equal to
So I went to a visual to try to figure this question out. I knew the parabola looked like that. I put all my focus on where these guys were.
Oh, so you just changed it.
And then I used my visual to help me answer the question. It tells me that I need to avoid being in between. I didn't really officially change the problem. I just looked at it from a different perspective. You don't have to do it this way. But the algebra in solving a quadratic inequality is not the same as the algebra in solving a quadratic equality. It's different. So I recommend getting a picture and answering it like that. Because we can know about a parabola, whether it opens up or down, immediately just by looking at the coefficient on the squared term. Okay. Question, yes?
So why would you put the -3, -2 in between the union in that one, but then in the second one, you don't need to use that?
It's a different question. And I can't be in between. Why can't I be in between?
Oh, so that
It would make me
has to
negative.
be in between them? In that one, the negative.
This is the in between, yeah.
Oh, okay.
So if I'm -3 and I'm -2, this is the in between, and I can't be. And here I can't be in between, but here I can. It's a different question. Yeah.
Gotcha.
Okay, I want to be positive, and this parabola is positive on the extremes and not in the in between. Another question, yes.
Yeah, how many changes the parabola open is the other one?
If the parabola opened down, then the part I would want would be the in between. Very good question. If the parabola opened down, you would want the in between part because that's where it would be positive at, and I wouldn't want the extreme parts. So be on the lookout for that. Yeah. All right. Great. And here's a hard one. Trick question. Tan of 2x. We need the domain for that. It's not an easy question. Just tan of x by itself. What's the domain of it? It's periodic, right? So the one part that we see when we draw the graph of tan. Sorry for just throwing it right in the middle here. Sorry. Negative what?
Like -5.
Yeah. Nothing wrong with that. Negative pi over 2 to pi over 2 is the part that we see. That's the fundamental period. But we know this thing continues on in both directions. And what it looks like is, kind of like an x cubed, y equals x cubed. But then it continues on. We can't just say the domain is just this. Officially, we'd be wrong. This thing continues on in periods of pi. The period on tangent is pi. Sine and cosine, the period is 2 pi. All right, great. Now, what's different about this is tan x. Y equals tan x. We don't have that. Okay, what does this 2 do for you as far as transforming your function? It's in there with the x. It's not on the outside. So if it was on the outside 2 times the tan x, that would be affecting your amplitude in this case, affecting your domain. But in this case here, your domain is still, your range is still minus infinity to infinity. It would affect your domain normally if it was on the outside. On the inside, it affects the period. Okay, but it's opposite of what you would think. You would think that times it by 2 would be like a stretch in the x direction. But it's opposite. Anything that happens with the x on the inside is opposite of what your intuition tells you. Anything that happens on the outside is exactly what your intuition says. If I add 7, I'm going to be moving it up 7. If I take away 7, I'm going to be moving it down 7. But if I multiply by 2, instead of stretching in the x, this will accomplish basically a compression in the x direction. It makes the period smaller. Okay, this 2 will make the period smaller. It's a x direction compression. It makes the period smaller by a factor of 2. All right, great. So when your period used to be pi, by you multiplying by 2 all your x values, your new period is half of that. When you say smaller by a factor of 2, it's like times by half. And so the period on this guy is pi over 2. Picture-wise, you wouldn't be going from minus pi over 2 to pi over 2. Shrink that in by a factor of 2. You'd be going from minus pi over 4 to pi over 4. Okay, so the fundamental, the one that we see, is minus pi over 4 to pi over 4. That's the one we see. But then there's all the other guys too. All right, all the other guys. And we have to come up with some kind of way to say all the other guys. Okay. Some mathematical way. I mean, I wouldn't mind you doing this. Okay, so what's the next one going to be? Going in this direction. And we can not equal. So we use parentheses. What would the next one be? Starting at pi over 4, where would you end up? 3 pi over 4, very good. Okay, great. Wonderful. And then starting or ending at minus pi over 4, you'd be at minus 3 pi over 4. But this thing's going to continue, basically. There's going to be union signs in between. Sorry, not commas. Union signs in between. It's going to continue on in both directions. And the pattern basically is, sorry about the way I'm trying to crunch this in here. The pattern basically is any odd multiple of pi over 4. Like the next is going to be 3 pi over 4 to 5 pi over 4, 5 pi over 4 to 7 pi over 4, and so on. And back to the other direction with the negatives. And so, I mean, there might be a more official way to say that. I'm probably fine with you saying just that. Basically, to say an odd is you fit this formula, 2n minus 1. That's an odd number for any n. And then I say that number times pi over 4. The positive version and the negative version. So any odd multiple of pi over 4 would be how I could say that. Any odd pi over 4, and then add the period of, I don't know the best way to say this. Add or subtract the period. This is bad what I'm saying here. I can't half do it. I need to do the whole thing. I can't half make an interval. Let me just say x that satisfy this. What am I trying to say here? X that satisfy this in the interval of any odd multiple of pi over 4 plus or what did we add this time? We just add the period. So plus or minus pi over 2. It's weird. Sorry. Jeez, that looks terrible. Yeah, I think on the typed up version, I have a better way to say this, but x in the interval containing, but not the endpoints, any odd multiple of pi over 4, even for the negatives. Where when I say any n, I mean integer, of course, sorry. Any integer n. And so that's not the best way to do it. But anyway, you get the point, and I'm perfectly fine, with this. Pattern continues on in both directions. I like that answer a whole lot better. Question, yes?
Ask something like this on an exam, wouldn't you just say, like, between the interval of 0 and 2 pi n?
I would restrict you. I wouldn't have this give me everything type thing. No.
So you don't really need to worry about that.
I'm telling you, I don't want you to have to worry about what I was trying to do here. I just want you to know that it can be done. Some like fancy way to say it all in one kind of nice phrasing. But you don't have to do that, no. Okay? All right, sorry I spent too much time on that. But you get the point. So if I ask you where a function is continuous at, you translate it to where is the domain. Okay. For all the functions that we're going to deal with. Oh, wow. Here's a typical question from an exam. If you go back and look at the old final exams, you'll see this question almost every one. And it'll be a question on your first midterm where basically I give you a function, but it's not just standard kind of, just regular kind of function. When you have this function like this, it's a piecewise function. It changes its identity, right? For certain values of x, it's one thing. For other values of x, it's totally something different. Okay? And so it's piecewise. And what's desirable is I want to know, okay, well, what's going to happen so that this particular function is continuous everywhere? See, this function has places where it could be potentially broken at. It could be broken at 2. It could be broken at 4. Maybe the left doesn't equal the right at 2 or at 4. And so what I need to do is be able to find out, okay, here's some constants A and B. Figure out what these constants need to be so that the function isn't broken. I want the function to be continuous everywhere. And so that gets translated to be, not broken. And so I don't want it to be broken. And so continuous everywhere means that, okay, even away, so I have this number line, which is my continuum of all real values, and I really get to focus my attention on 2 and 4, okay? And here's what I do. Whenever I see a piecewise function, I do the following. I draw a number line. I mark off the places where it's maybe, broken, and I write down what the function is in the different intervals. Like I have instead of this formalized way of writing it, I prefer to think about it like this. My function is 1 plus x squared, as long as I'm smaller than 2. In between 2 and 4, my function changes. It's not this parabola anymore. It has this different identity. Right? It changes to become x plus a plus b. In between 2 and 4. After 4, it changes its mind again. It becomes something else. Okay? Schizophrenic is like what I think about. Changes its mind, becomes something else. Depends on what day it is. It depends on what x value it is. Okay? Piecewise defined functions. So, as long as I'm one of these functions, I shouldn't have a problem about being continuous, right? The first one is a parabola, continuous everywhere. I don't have to worry about that. A line is the middle part, continuous everywhere. Now the square root I should have to worry, but as long as x is 4, I'll make sure that the a is something that'll never go negative. And so it's not about what happens, on these intervals. It's really about what happens where these guys meet up. I am going to force them to agree. Where it's going from the left is going to be where it's going from the right, and the function value is going to be there too. That's what continuity is all about. So that's the question. Where is the function going to from the left, and where is it going to from the right at these broken parts of your interval? So officially, there's the limit as x goes to 2 from the left for this particular function. And what I'm saying basically in my shorthand drawing is that I am going to use the function 1 plus x squared to find that limit. I could do it without a calculator or without a picture, because I can just plug in. Whenever I have a limit, the first thing I want to try to do is plug in. Sometimes I'm not allowed to, but for this, there's nothing restricting me. There's no division by 0. And so I'm just going to plug in, and I can see that this particular parabola is headed towards what y value? 5. Very good. My parabola is headed towards y equals 5. As x goes to 2 from the left, y goes to 5. Okay, well, as x goes to 2 from the right, they have to meet up. So my line needs to also go to 5 if I'm going to be continuous everywhere. And so as I go towards 2 from the right on this particular function, I'll be using the line, which is titled x plus a plus b. Okay? Still, nothing to stop me from plugging in x equals 2. Nothing to stop me. So I get 2 plus a plus b. So here is my right-hand limit. Here is my left-hand limit. If I'm supposed to be continuous everywhere, particularly at x equals 2, those two better equal each other. 5 better be 2 plus a plus b. It doesn't tell me exactly what a and b are, but it gives me a relationship between a and b. 2 equations, 2 unknowns. I need another equation. I need another relationship. That's going to come from what happens at x equals 4. And then together I can untie and figure out what exactly a and b are to make this happen. Okay, so let's do this. Let's go to, let's simplify this somewhat. Let's take this 2 over and say that these guys, A and B, they need to add up to 3. That's a better way to say it. Nothing wrong with 5 equals 2 plus A plus B, but I like that way better. They have to add up to 3. That's half the story. The other half comes from what's going on at x equals 4. All right, from the left-hand side, what are you going towards? All right, from the left-hand side, you'll be using that line again. And it's x plus a plus b. So you plug in a 4, and you get 4 plus a plus b. from the right-hand side. You're not using a line. From the right-hand side, you're using the square root. Officially, let me just go ahead and be formal here and put the f of x in there, and then later put that guy in there. Okay, you don't have to be so formal. I need to see something though. I just, this drawing technique, I need to see more than just a drawing and arrows. You know, I'm going to need to see, you know, limb and left, and I'm going to need to see that technically. So for full credit, just showing your work, I need to see more than just a. So you have to work on being able to write it up a way that, you know, and get your full credit when it comes time for partial credit. And so just a drawing is not enough. I need to see official limits, left-hand limits, right-hand limits, and you saying that they're equal for continuity. And so just plug in x equals 4. The root of 4 plus 5a. All of that underneath the same root. These two guys better equal each other. Now, we do have two equations, but our two equations aren't linear. If they were both like of this kind of, you know, where you're able to say, you know, a and b is equal to, you know, if they were both like that, then it'd be a lot easier to solve. Like, it'll be like what you had on your quiz in recitation this week. But it's not like that. One's linear, the other one has this root in it. Okay, so system of equations is not going to solve. We can't just eliminate the variable. But another technique to solve when you have two equations is substitution. We know what a plus b is. And conveniently, a plus b shows up in that second equation. A plus b better be 3. We know that. Let's sub that in and replace the a plus b from a second equation with a 3. And now we have a single variable equation that we can solve. Okay, 4 plus 3 is 7. So 7 is supposed to equal the square root of 4 plus 5a. Now go solve for a. Solving equations in the middle of a calculus problem. Work on it on your own, on your paper. Tell me what you get. When you get it, just raise your hand. Don't yell it out. I'll come by and check. I need you to tell me what a is. And then go ahead and get what b is as well, knowing that they have to add up to 3. Yes, that's right. Yeah, it's okay. Yeah, I mean, you know, this notes, you don't have to officially have some nice write-up. Good, right? All right. So it seems like you get a consensus here. Wonderful. Yeah. Okay. Yeah. So, you know, what underneath the root needs to be 49, right? Because the square root of 49 is exactly 7. So you do that and you get. Yeah. Good. All right. So 4 plus 5a better be 49, squaring both sides. And so, so a better be 9 to make that happen. And if they have to add up to 3, and you already have a 9, the other guy has to be a negative 3. Negative 6. Good stuff. Okay? Expect something like that. Okay? And you'll see more difficult ones than that. I think I want to keep that for some reason. All right, so I'll see you guys on Friday, and we'll start with this intermediate value theorem.